In this video, you are going to learn about isotopes. As we have seen before, within the nucleus, we can see positive charge, and that is the proton. However, inside the nucleus, how can you have all positive charge get together? Because the positive charge is going to repel the positive charge. So in this case, there is a kind of a super glue that here is called neutrons. So the function of the neutron, if you look at it in this purpose, it's just to glue them up so the positive can stick together. Okay, so the question is, can we have more than of what we need? And the answer is yes. For example, if I have 3 positive charge here, supposedly if I have 3 neutron particle, the super glue, that's enough to glue them together. However, we can have extra super glue. That means we can have extra neutron. So in this case, I can have, let's say, 4 neutrons. If you look at this case, they both have the same number of protons. That means they are the same element, but with different number of neutrons. We call this isotopes. Isotopes. That is, for the elements or for the atoms that have the same number of protons, but with different number of neutrons. Let's look at this one. Magnesium. Magnesium is atomic number 12. And if we write it this way, this is the mass number, is the number of protons plus neutrons. So in this case, if I write it Mg, the 12 over here, 24 over here, that means I have 12 protons for this Mg. And by the way, the atomic number should be fixed for the same element. And there are 24 altogether. There are 24 particles, okay, or we can call that a mass number. So how many neutrons do we have? Over here, this number, the mass number minus the number of protons, that would be equal to the number of neutrons. Doing the same calculation, I can find out that if I have 25 over here, let's write it over here. If I have 25 and I have 12 over here, how many neutrons? The mass number minus the number of protons, that is equal to the number of neutrons. And over here, there were 13. So these are called isotopes because they have the same number of protons, but with different number of neutrons. Okay, so magnesium, we can find isotopes. In fact, many elements, we can find isotopes. So here is a clear picture of showing the atomic number, which is the same as the number of protons. The mass number is usually written on top. So we can do the calculation and we can find out how many neutrons. And very rarely they are going to write down the number of neutrons. They always write it in this way. Probably they want us to do calculations. Okay, or actually we are running out of space to write everything. For example, this corner is used to write something else. In this case, the charge. Okay, so how do we calculate for the number of neutrons? Number of neutrons, that is equal to the mass number minus the number of protons. Okay, so in this case, there are 2 neutrons over here, equal to 4 minus 2. Okay, so let's look at some elements that is with isotope forms. Let's look at hydrogen. There are 3 different types of isotopes for hydrogen. The very popular one that we usually see is this one over here. That means inside the nucleus, there is no neutron because no neutron is needed. There's only 1 positive inside. We don't need any neutron. We do not need any super glue for it. And there's one electron outside that is running. Okay. So as for atomic mass, that means the mass of everything. The mass of neutron plus the mass of proton plus the mass of electron. That is called the atomic mass. In this case, atomic mass for hydrogen with no neutron, and atomic mass is 1.0078. This unit over here is called AMU, that stands for atomic mass unit. And usually that is equal to the unit of a proton or a neutron particle. And this little thing over here, because we add the electron to it, that's why it's more than one. Okay, let's look at the other form over here. The isotope form of hydrogen is called deuterium. Deuterium is with one neutron. So this one, it is protium. And if you want to look at deuterium, you can see one proton plus one neutron. Usually use the letter N to represent for neutron. That's inside the nucleus. And one electron that is outside running around. Okay. So in this case, the atomic mass will be equal to the mass of the proton plus the mass of the neutron and plus the mass of the electron. And therefore, it is over here. Here's the atomic mass. And the third type of isotope for hydrogen, it is called tritium. Okay. And by the way, reacting with oxygen, it is called heavy water. Okay. So about 20 to 30 years ago at Brookhaven National Lab, there is a leak of heavy water. That means this isotope is leaking out. That's why they closed the nuclear reactor at Brookhaven National Lab. Okay, so over here, we can tell that the atomic mass is over here. Okay, since there are more than one form of isotope, and how do we know the average weight of the isotope? So what we need to know is the abundance. That means how much they exist in nature or in that mixture. Okay, here is called abundance or percentage. In this case, more than 99.9%, it is just protium. And certain amount, well, significant enough, that is deuterium. And very small amount is so small, well, just put the word trace of it. Okay, it is tritium in it. So how do we calculate the average atomic mass of these three isotopes, or in general of isotopes? Here is the formula. The average mass of the isotope will be equal to the fractional abundance. That means 0 point something. It should be less than 1 with this number, times the isotopic mass. Okay, let's look at an example. With boron, boron is atomic number 5, but we may not need that for the calculation. All right, so 19.9% of the boron is with the atomic mass of 10.0129 AMU. The rest, that means 80.1%, is with the mass of 11.0093 AMU. How do we calculate the average mass of these isotopes? Okay, so we try to follow this formula over here. Fractional abundance of the first one is 19.9%. But how do we write it? We write it in decimals. 19.9% is the same as 0.199. It's the same. This one just written in percentage. This one is in fraction or decimal. Okay, multiplied by the mass of that atom is given over here. So we multiply by that and the sum. So we add it to another one. Over here, the abundance or the fractional abundance or the percentage, it is 80.1%, which is same as 0.801. Remember, this number cannot be bigger than 1 because all the percentage, it should add up to be 100%. Okay, so that times the atomic mass. So what we get for the average is 10.81 AMU. All right, let's work on some exercise, see if we know how to calculate the average mass for isotopes. Let's look at this one. An element X has 3 naturally occurring isotopes, and the abundance and the mass are given in this table. Let's calculate for the atomic mass. The average atomic mass. Okay, so according to our formula, we should use the abundance, but we have to put it in decimal point. Okay, I cannot just use 74.22. Here is percentage. So what I can do is the average will be equal to 0.7422 multiplied by the atomic mass corresponding to that abundance, that is 220.9. Okay, I add to the other one. See, over here we have 3 isotopes, and from the previous calculation of boron, we only have 2 isotopes. So we should expect to have 3 different terms here. Okay, 12.78%, it is, I cannot just like write 12.78. I have to put it in decimal form, that is 0.1278. and then multiplied by 220.0. And I would like to add the third term over here. It will be 0.13, so that will be 13% times 218.1. I'm going to use my calculator and see if we can get any correct answer. It would be 0.7422 times 220.9 plus 0.1278 times 220.0 plus 0.13 times 218.1. From my calculator, what I get is 220.42. Okay, yes, at least we can find some answer that is matching. Okay, we just have finished doing an example of isotope calculation. Now let's see how we can detect isotopes, how we can measure isotopes. Okay, so here is a device that is used to detect isotopes. What happened is, over here, the sample over here, somehow we have to disintegrate the atoms into its atomic form. For example, if it's from a piece of metal, okay, or a piece of solid, that is my unknown sample, how do I know what are the types of isotopes that are in it? Or what is the element that is in this unknown solid, and so on. So what we can do is, we can knock out the atoms one by one by using an electron beam. So when an electron beam or other type of beam, it can be a plasma, when something bombard on it, so the particles can fly out. The atomic particles can fly out. When these particles, they are hit by a charged beam, then itself will carry some charge. With some charge and some mass, some weight, it can go through an electric field and make this charge go faster with a controlled speed. Once the charge can go under some velocity and going through a magnetic field, different mass is going to change to different radius. That's how people can detect the isotope. Let's say the heavier one, where should the heavier one go? The heavier one is going to go over here. The lighter one is going to go further. Okay, so that is how it is detected.